Hi, my name is Eitan Tashi. I'm the lead gemologist with our education department here at Professional Gem Sciences Laboratory. Welcome to this introductory lesson of our flagship diamond educational course. Whether you're taking this course with us online or in person, we're very excited to have you with us as you grow in your career as diamond professionals. So thanks for joining us. For this first session, I want to introduce you to some of the properties of diamonds. This won't be the exhaustive list. We'll go through many more properties in more detail later in this course, but I think this is a great place to start from during this time of incredible change in our industry. I get asked all the time what I think the future is for diamonds. Well, I can tell you with certainty that the future is bright, and I think that this section will help establish why. These initial properties that we'll discuss today are going to help us define why diamond is so special, understand why it's so ideally suited for use in jewelry, and then also give us the foundation from which to discuss more about properties as we build in later sections. What we ultimately want you to start thinking about here is how to approach properties of a material in a critical way, just as a gemologist would. This will not only help you throughout your career, but it'll also be the basis for understanding diamond's inherent value from multiple different angles and perspectives. We'll start with a discussion of diamond's crystal structure. Here you can see a polished diamond next to a rough diamond. We'll talk about carbon bonds. From there, we are going to pivot to discussing diamond formation and understand a bit about how diamonds are mined. We're then going to examine diamond's hardness, toughness, and luster. These are some of the properties that do make it so well suited, again, for use in jewelry and set it apart from the other precious stones. So let's dive in. What does it mean to be a diamond? There are dozens of colorless crystals that exist artificially and naturally in the world. Why is diamond different from all the others? Much of that difference comes down to their physical properties. In the study of gemology, we catalog these properties in order to identify and differentiate one material from another. These physical observations enable us to differentiate natural diamonds even from lab grown as well. Ultimately, it's these properties that dictate whether a substance is suitable for use in jewelry or if it's befitting other applications. In this example here, you can see three color stones. They all look similar, but they have subtle differences in one of their properties, which is called dispersion or fire. Diamond has a particular pattern of dispersion that, when you know what to look for, will help you identify it visually as different from the other materials here. And this really encapsulates the crux of what everything comes down to. Here you can see two rings. Uh, Set into the gold, you have one of them is a diamond and the other is a CZ. The CZ is on the right and it appears dull after years of wear. It's been scratched and abraded, and this is actually just through normal wear, through no fault of the owner. By contrast, the diamond on the left remains quite bright and white. We're going to start here with our analysis of crystal structure. A crystal is a term used to describe solids that have an ordered and repeating structure. They often form irregular and repeating geometric shapes. These repeating patterns form what's called a lattice and grow in a generally ordered shape and appearance. So obviously diamonds and rubies are crystals, but also things like snowflakes and even table salt, which we don't think of so often, are crystals as well. If you combine two or more crystals together, you get a material that is called polycrystalline. Nature tends to make a lot of these materials. So things like rock and clay are polycrystalline. And some examples of polycrystalline gems that you would see on a regular basis are things like jadeite and turquoise, just to name a couple examples for you here. Diamond is unique in the world of crystals in that it is a crystal that, in its purest form, is comprised of only one element, carbon. Most other gemstones that we think of, things like emeralds or quartz, garnet and sapphire, these are all comprised of multiple elements on the periodic table. Aluminum oxides, silicon dioxides, not so with diamond. So diamond, again, in its essential structure, is just carbon. Carbon is an amazing element. So all life on Earth is carbon-based life. I like to ponder sometimes the symbolism of carbon-based life adorning itself with carbon crystals and think about the implications of that. Diamonds form in the cubic crystal system. You can see an example of that here, along with some other shapes. The typical shape that it forms in is called an octahedron. Here you can also see some other crystals again. garnet, beryl, just to name a couple. It's diamond's tight carbon bonds in the cubic crystal system that make it so strong and tough. So it's ultimately one of the reasons, again, why it's so ideally suited for use in jewelry. Actually, I always found it super fascinating and one of those interesting contradictions in nature that if we reorganize those strong carbon bonds, change the crystal structure ever so slightly, you go from one of the hardest materials in nature, diamond, to one of the softest, graphite. Graphite, as you see here, like diamond, is just pure carbon chemically. Its only difference is its crystal structure. Graphite's obviously so soft that rubbing it against the surface of paper will leave streaks of itself. And it's for that reason that we use it as lead for pencils. Now, as opposed to that block of graphite, you can see here many examples of diamond crystal rough. It can form in a number of different shapes, the most regular, again, of which is called an octahedron. Here's one example. Essentially, what this looks like is it's two pyramids that have been stacked together at the bases. So that is what an octahedron is. You also have these cube shapes. They're less common. You also have barrel shapes, a much more common shape. This will generally yield what's called a fancy shape once it's been manufactured. So this is any non-round shape is called a fancy shape. And then lastly, you also have what's called a macle. Here's a triangular piece. These are all known for being quite flat, and it's caused by distortions in the crystal structure during the growth formation process. What all these shapes have in common is that, very typical to diamond, they have triangular faces. So these faces, they tend to grow with also triangular features on them called trigons on the surface. We'll actually see quite a lot of examples of this when we start looking at inclusions and doing grading. But I already want to expose you to these terms so that you know what natural features are, you know what to expect to see in this course and then throughout your career. And then you can also contrast it when you see unnatural features that are man-made from the laboratory. Diamonds form deep in the Earth's surface, so much, much deeper, in fact, than most other minerals in the world. So deep that it's theorized that they form in the Earth's mantle rather than the upper crust region. So those depths, they create tremendous amounts of heat and pressure. And it's under those conditions where diamonds take shape. Because of those immense depths from where they form underground, diamonds actually come to the surface through volcanism. Most of the diamonds that come to market today are mined from ancient volcanic tubes, long since dormant and extinct. These are referred to as diamond pipes. Diamonds are found in a material called kimberlite. So this is a type of hard rock where diamonds are generally mined out of in these pipes. Kimberlite, it's named after Kimberley, South Africa. This is the place where diamonds were first discovered in pipes. Until then, diamonds were actually all generally mined from alluvial deposits. So while we're on the topic, where do diamonds come from? The first thing that tends to come to people's mind is Africa. While this is one of the continents where diamonds come from, it's not the only one, and it's probably only represents about 50% of global diamond production on any given year. Many other countries are also producers of diamond. If we're speaking about historically, diamonds all actually came from India. All diamonds that are mentioned in famous books or appear in famous jewelry in the pre-industrial period, so pre-industrial revolution, came from one source in Golconda, India. It stays that way pretty much until diamonds are found in Brazil in the 1700s. And diamonds aren't discovered in Africa until the late 1800s and the early 1900s. Really, things start to kick off with large-scale mining. Today, those mines in India have long since been exhausted. Other countries like Canada and Russia are also very large producers of diamonds today. Yeah, on the topic, I don't know if you've ever seen or heard the show Ice Road Truckers. One of the seasons is devoted to a very remote mine in Canada where the Ice Road Truckers are going to deliver supplies that basically support the mine and mining facilities. So just something that I figured I would mention for you anecdotally. In fact, there are even diamond pipes in the US. It's a place called Crater of Diamond State Park in Arkansas. I took it there a couple years ago and had a great time. I didn't find any diamonds, but I did spend the day mining and getting a feel for the mining process and also the thrill of searching for diamonds. It's not in yellow on this map of diamond producing countries because they're not commercially viable quantities of diamonds found there. However, people do find stones there periodically on a 1-2 basis, and occasionally even something quite large and significant. So, as I mentioned, historically diamonds were all mined from erosion zones along the periphery of an exhausted volcano. This is called alluvial mining again. Here you can see an example of it. It is still practiced today, but far less frequently, as it's much less cost effective, essentially. With the advent of technology and innovations in mining, humans have the ability to identify and dig deep columns in the earth where there was once volcanic activity in order to unearth concentrated pockets of diamonds. It's these dense concentrations that's really so crucial to justify the immense costs associated with mining. Mine yields can vary dramatically. So, this is the amount of diamond that is yielded from a particular mine. But a good rule of thumb is that it requires moving about 250 tons of earth to produce 1 carat of diamond. That's a phenomenal amount of dirt to displace. Let that sink in. 250 tons of earth. Wow. Actually, I also recall one time having a client when I was working on the retail side of things express to me concern about an eye visible feather that he had noticed in a diamond he was considering buying. He was worried that the feather was a crack and that it would cause the diamond to break. Essentially, what I did is I explained to him that he's looking at a billion-year-old crystal that formed in a heat and pressure environment where most natural materials would melt. It then came to the Earth's crust in a volcano. From there, it was blasted out of the ground using heavy explosives, manufactured with lasers and cutting equipment that's spinning, close to 100 meters per second. I told him that if the diamond can endure all of that in order to be here today, then you really don't have anything to worry about regarding the feather. Needless to say, he was quite satisfied with the answer. Here actually is another image that I just love that really speaks to the scale of diamond mining. This is of the Mir mine in Siberia, Russia. This is the largest man-made hole ever dug. You can see it from space. To give you a sense of perspective and scale here, you can notice the city that's adjacent there. So this is a city of approximately 30 to 40,000 people. It exists only for this mine. It's again in the middle of Siberia. And it looks like you could actually fit the entire surface area of the city into the mine's pit. The other mine adjacent that in the picture is the Diavik mine in Canada. That's located again in the far northwest territories, very far off the beaten path. There is also a third method for mining that we didn't get into. This is called deep sea mining. It's less practiced because it requires actually special technology. One place that produces a fair amount of deep sea diamonds is Namibia. What's the thread pulling all of this together? All of these mines really emphasize how difficult it is to get to diamonds. They're far off the beaten path in many places on the earth and require immense amounts of labor and equipment in order to do the mining process. So that was a bit about where diamonds form. Now I want to shift gears and speak about the properties that make diamonds so special and so ideally suited for use in jewelry. The first one that we are going to talk about here is hardness. Diamond is a 10 on the Mohs hardness scale. This is a scale that quantifies the hardness of materials. Hardness in gemology refers to how resistant a material is to scratching. So the scale, it goes from 1 on the low side to 10 on the high side, 1 being the softest material, 10 being the hardest. So for reference, something that we think of as being one of the hardest substances around, right? Titanium. It's actually somewhat soft compared to gemstones. Titanium, it can be quantified on this list, and it has a hardness of a 6, meaning that a diamond would just cut through it like butter. Steel, another hard material, depending how it's alloyed, has a hardness of anywhere between 5 and 7. Even your fingernail could be quantified on the Mohs scale. It has a hardness of around 2.5, meaning that we can easily scratch something that is a 2.5 on the scale, or something lower, a 1 or a 2. So materials like gypsum or fluorite, calcite as well, while pretty, they're not very suitable for use in jewelry, since they're so soft that they can be scratched by almost any material that they would come into contact with. But a 1 to 10 scale doesn't really elaborate just how much harder diamond is on the scale than, let's say, a sapphire. So a sapphire, it's one of the gemstones that is a 9 on the Mohs scale of hardness. Now, that sounds like it's close, right? 9 and 10. But in reality, a 10 is exponentially stronger and harder than a 9. So, in terms of a diamond's hardness, it's actually literally off the charts. Again, this is a great reason for it to be used in jewelry. Fluorite, it's actually one of my favorite crystals. Here you can see a great rough specimen illustrating how they crystallize. They have these incredible shapes and colors. It's also actually the state gemstone of Illinois, so my home state. And unfortunately, it's just very soft. So here you can see a vintage ring that's set with a piece of fluorite that's been super scratched and abraded just through normal wear. Again, it doesn't mean that you can't use it in jewelry, but that you just need to have special care that you apply when you set it, when you handle it. And maybe it's even one of those things that it's much more better suited for earrings or a pendant as a piece of jewelry rather than a ring, since a ring tends to take a lot more of a beating. So what else can we just learn from this chart? Well, for one thing, again, only a diamond can scratch a diamond. I want to point that out. Only a diamond can scratch a diamond. Let's also say that hardness is resistant to scratching, but not to chipping. Resistant to chipping, this refers to the next property that we'll review together, which is toughness. So in addition to a diamond being exceptionally hard, diamond is also incredibly tough. So it's not prone to chipping or breaking. It's quite resistant to it, in fact. But again, this doesn't mean that it's indestructible. On the contrary, it can chip, and it does. And there's certainly certain points where it's more likely to chip and more vulnerable. So, for instance, places like the girdle, the culet, or points and corners, as you can see here. Here I actually marked the chip in the corner of this princess cut. So these are places where a diamond is most likely to get chipped, or even smaller than a chip, nicked or abraded, if it's going to be nicked or abraded. So what does that mean? It means that when you're handling a stone from these points, either in this course or during your career, you should take extra care from these areas. But otherwise, we are talking again about a very durable material. Related to this notion, it also has what's called a cleavage direction. This is somewhat akin to a grain of wood, that if you would hit it at just the right angle, it would split the wood. Well, the same is true for diamond. Hit it at the right angle and it'll split. They use this in the cutting process, actually, to do what's called cleaving a diamond. We'll get more into that when we talk about manufacturing. But yeah, so how you might see that is if you were to cut or polish a stone against the grain, you would feel resistance. Change the angle, and now you would be able to polish the stone. This is again more relevant for a cutter, but it's something that we want you to know about, that it exists as diamond professionals. So what other ways are diamonds tough? Well, they're very resistant to chemical burn. This is not the case with most gemstones. So think of things like opal or pearl. These could be dramatically altered just by coming into contact with regular household cleaning materials. Diamond, on the other hand, it can take a bath in acid and it'll emerge just as shiny and bright as the day it was polished. Sometimes jewelers even use this as a test to check if a material is diamond or CZ, in fact. The last point that I want to make related to diamond's toughness is that it also disperses heat really well. So this is relevant during the setting process when a hot jeweler's torch is near the diamond. It means that the heat from the torch will generally not damage the diamond at all. Okay, and the last property that we're going to cover in this introductory section is luster. Diamond can take quite a polish. It has what we refer to as adamantine luster. Luster in gemology, it refers to how well the surface of a material can be polished, so essentially how shiny it can become. It aims to describe both the quantity and the quality of reflected light on a stone's surface. So some of the terms that we use to describe luster in gemology include things like dull, waxy, greasy, resinous, vitreous, metallic, and then right at the very top, adamantine. Adamantine, it comes from Latin root word for diamond, which is diamos, or adamas in the Greek. So to the ancient Greeks, the word adamas literally meant something that was unconquerable or untamable. We also get the word adamant from the same root word, actually. How appropriate that thousands of years later, the word will actually become to be associated with diamonds, and through that association, to love, the most unconquerable emotion of the human experience. Funny enough, many people are familiar with the word adamantine from the world of comic books, actually. If you recall the Marvel superhero Wolverine, he has claws and a skeleton made of adamantium. So this is a fictional metal alloy. It doesn't exist in real life, but in the comic book, it's indestructible. It's one of those fun instances where art and pop culture draw on the lore of the jewelry industry for symbolism. So diamond has the highest luster possible on the gemological scale, but it actually doesn't start its life that way. And as you can see here, you have a rough diamond, and it generally has a dull or waxy luster when it's mined from the ground. And it's really through the skilled craftsmanship of the diamond cutter that the stone achieves its best form, bringing a diamond in the rough to its ultimate potential. Diamond can achieve also what's called a perfect polish. So essentially, what this means is that it can be incredibly, incredibly flat on a molecular level. This is again one of those interesting properties related to diamond that just other crystals don't have. I love this image so much. You know, a rough diamond in the center, and then you have two polished diamonds on either side. And the polished diamond on the left, it's an ideal cut, while the polished diamond on the right, it has quite a lot of dark areas in it, if you can see that. These are called extinction. And it really illustrates again how diamond starts out its life and then which direction it can take based on the trained eye and the skilled craftsmanship of a good diamond cutter. But more on that later, but just wanted to point that out here. It's also actually an interesting point to make that the jewelry industry is not the only sector that uses diamonds and is buying diamonds in the global marketplace. So diamonds are an important material in industry. You have diamond-tipped drill bits and diamond dust found throughout masonry equipment and in the mining sector. Even actually in dentistry, they use diamond burrs and grinding tools quite widely. Diamond is also garnering attention from the material sciences sector for its heat dispersive qualities that we mentioned earlier. So specifically, as a potential alternative to silicone chips in computing. So what other applications these special materials hold for us, really only time will tell, but certainly the future will continue to shine bright for diamonds. Why am I telling you all this as we close this introductory portion of the course? Again, it's reinforcing diamonds' inherent incredible properties, and it shows the demand for them beyond just our industry. Perfect. So we have a great foundation on which to build from. What we've done in this section is we've taken a good look at a few of the key properties of diamonds that make it so well suited for use in jewelry. Things like its exceptional hardness, toughness, luster, all these attributes make it really the perfect commodity that can be worn in everyday life. We also touched on where diamonds are found and how they're mined. This helps frame why diamonds, where diamonds come from, excuse me. in the earth, and then again frames why the mining process is so costly. We've also seen that diamonds are coveted in industries well beyond the jewelry industry. What again we're ultimately building here is that understanding of diamonds' value. We'll expand on all of these topics again in later sections in this course, but we now have that foundation on which to build from as we're going to shift gears and now start to talk about diamond grading and evaluation in the coming sections. Likewise, I encourage you to think about diamonds with creativity and an open mind. This section is just the beginning, and the applications go far beyond. So thanks for being with us here for this first session, and we'll see you in the next session. Take care.